In this video, we will present about orthogonal basis.
We will discuss about the definition of orthogonal basis, the theorem, example, and counter-example that related to orthogonal basis, the theorem from Grant-Smith and example, and lastly the references.
An orthogonal basis for a subspace W of Rn is a basis of W that is an orthogonal set. For example, determine whether B1, B2, B3 is an orthogonal basis for R3 if the following vectors are given. The first step is to show that every pair of vectors from this set is orthogonal. B1 dot product B2, then we get the answer of 0. Next, B1 dot product B3, then we get the answer of 0. And then we repeat the same step, B2 dot product B3, then we also found that the answer is 0. So the vectors B1, B2, and B3 are orthogonal. The second step is to show that this set of vectors is a basis for R3. So firstly, we write it into an augmented matrix. Then we operate an elementary row operation by Gaussian elimination to reduce it into row echelon form. Then we found that this set of vectors is linearly independent, thus it is a basis for R3. Then we can conclude that this set of vectors is an orthogonal basis. Now let us look at the theorem. Let a set of vectors be an orthogonal basis for a subspace W of Rn, and let vector W be any vector in W. Then the unit scalar C such that are given by
We take a look at the example. Find the value of x, y, and z if any, such that the set A is an orthogonal basis for R3. Given that the set A consists of V1, V2, and V3. V1 dot product V2 equal to 0, V1 dot product V3 equal to 0, and V2 dot product V3 equal to 0. So, to find the value of x, y, and z such that the set A is an orthogonal basis, we need to solve the system of linear equations. X plus 2y equal to 2, negative 4x plus 2z equal to 2, and negative y minus z equal to 4, which the system of linear equation will form of the augmented matrix. Transform the augmented matrix to row echelon form REF by using elementary row operation ERO. Then, translate the row echelon form matrix to the associated system of linear equation. X plus 2y equal to 2, negative y minus z equal to 4, and negative 6z equal to 42. We use the back substitution method to find the solution. Starting by the last equation, isolate the variables and replace it in the equation above. Do this process until the first equation. So the solution is x equal to negative 4, y equal to 3, and z equal to negative 7.
Next, we do a counter-example to prove either the set is orthogonal basis or not by following these three steps. Step 1, to show the spanning set. Step 2 to show the linearly independent, and step 3 to check orthogonal basis. For step 1, we show A span R3. Let A, B and C be the scalar. Then construct augmented matrix. Reduce to REF row echelon form by using elementary row operation ERO. After complete to REF, we can see there are 3 leading entries for each column. By using back substitution method, we can get the value for A, B and C. Since the system is consistent, then the A span R3. Consistent means at least have one solution. For step 2, to show A is a linearly independent, we can use the same step as we want to find the spanning set but change the answer into 0. By using back substitution method, we can get the value for A, B and C. Since A, B and C equal to 0, so A is a linearly independent. Then A is basis for R3. And lastly, step 3 to check either orthogonal basis or not. We have vector 1, vector 2 and vector 3 that we get from basis. So, we use dot product method. B1 dot product B2 equal to 1, B1 dot product B3 and B2 dot product B3 also equal to 1. Since the answer is not equal to 0, then this vector is not orthogonal basis.
Okay, now we're gonna learn about the Gram-Smith process. Okay, it's actually a theorem to find an orthogonal basis. In this theorem, it states that let x1, x2 until xk be a basis for a subspace W of Rn and define the following. So in this theorem, it states how to find the vector 1, vector 2, vector 3 until vector k. So you have to follow the formula only. Then for each I equal to 1 until k is actually a vector 1, vector 2 until vector I is an orthogonal basis for Wi, or vector 1, vector 2 until vector k is an orthogonal basis for W. To make you more understand this theorem, let's look at example 1. Let W equal to spanning set of x1 and x2, where x1 is equal to 1, 1, 0 and x2 is equal to -2, 0, 1. So, the question asks, by using the Gram-Smith process, construct an orthogonal basis for W. So, how are we going to solve this question? Solution for this question is V1 equal to x1, that is 1, 1, 0. This is because in the theorem it states how to find vector 1 is by equal to x1. So next is how to find vector 2. To find vector 2, we have to get the value of x2 and vector 1. So we have to insert the value of x2 and vector 1 into the formula, and lastly you will get for vector 2 is equal to -1, 1 and 1. Then as a conclusion, vector 1 is equal to 1, 1, 0 and vector 2 is equal to -1, 1 and 1 are orthogonal basis for W. But if you didn't confident with your answer, you can check by using the dot product. So you can do the dot product between vector 1 and vector 2, and the answer you will get if it is an orthogonal basis is 0. So when you get equal to 0, that means your answer is correct. But if you didn't get 0, that means there must be something wrong with your answer. You must check it back. So, as a conclusion, we can conclude that vector 1 is equal to 1, 1, 0 and vector 2 is equal to negative 1, 1 and 1 are orthogonal basis for W.
Example, find the closest point to X in the subspace W spanned by V1 and V2. You are given three column matrices which are X, V1 and V2. For the solution, if V1 product V2 and the answer that you get is 0, then V1 and V2 is an orthogonal set. Neither V1 nor V2 is 0. This means that V1 and V2 is linearly independent. And since W is spanned by V1 and V2, we have that V1 and V2 is orthogonal basis for W. Then, by using the theorem, you need to use this formula where you need to substitute the value for X, V1 and V2. And you will get the answer is 1 over 2 V1 plus 3 over 2 V2. But you need to substitute the value for V1 and V2. The value for V1 is 3, 1, negative 1 and 1. While for V2 is 1, negative 1, 1 and negative 1. The value for V1 and V2 we took from the questions. Then the final answer that you will get is 3, negative 1, 1 and negative 1. The next example is to find an orthogonal basis for the column space of the following matrix. You are given matrix A. For the solutions, let A be the matrix in the problems. The first column will represent x1, second column represent x2, and third column represent x3. And let V be column A. Then we need to find an orthogonal basis for V. In order to use Gram-Schmidt, we need a basis for V. By definition, x1, x2, and s3 is a spanning set for V. But we need to know that x1, x2, and s3 is linearly independent before we know it's a basis. To check that x1, x2, and s3 is linearly independent, we need to reduce matrix A to REF. First, we need to do ERO until we get REF. Then, from the column, we know that x1, x2, and s3 is linearly independent. Then, by using Gram-Schmidt, V1 is equal to x1. The value of x1 we took from the first column of matrix A. Then, to find the value of V2, we need to do this formula in order to get the value for V2. Then, you will get is x2 plus V1, but don't forget to substitute this value. When we calculate, the final answer that you will get for V2 is 3, 0, 3, negative 3, and 3. For V3, we need to do this formula in order to get the value for V3. Then you will get is x3 minus 4V1 plus 1 over 3V2. Don't forget to substitute this value. Then the final answer that you will get for V3 is 2, 0, 2, 2, and negative 2. Then from here, we know that this is the value of V1, value of V2, and this is the value of V3. Then V1, V2, and V3 is an orthogonal basis of the column space of the matrix. But in order to make sure that your answer is correct, you can recheck your answer by using dot product. If V1 dot product V2 and the answer that you get is 0, then this is an orthogonal basis and you need to do the same operation for V2 and V3. If all the answer that you get is 0, then V1, V2 and V3 is an orthogonal basis.